Hey everyone, welcome to the lecture for 6.1. We'll be covering the standard normal distribution today. I've created an Excel worksheet for us. However, I want to start the lecture off just kind of doing things manually. So the normal distribution is a continuous probability function, and it's concerned with events that are distributed according to the PDF f of x equals, wow, a lot, something very extra, right? So even though this looks very overwhelming, I just want you to think of it as the bell curve. It's also called the Gaussian curve. And basically, it's something we've seen so many times in our lives, right? So we have this kind of bell-shaped curve here towards the bottom of the screen. And we're given mean and standard deviation. So this is a case where we're going to be told, hey, our mean is blank and our standard deviation is blank. And then from there, we're able to make calculations, observations, analyses on the random variable x. So if x is known to follow a normal distribution, we're going to write this statement here. So as before, when we had the binomial, we only needed to know n and p. When we had the uniform distribution, we only needed to know a and b. For the normal distribution, we only need to know mu and sigma. So binomial, sorry. For binomial, we had n and p, right? The number of trials, the probability of success. For uniform, we had a and b, the start and stop values, or the high and the low. And then for normal, we have mu and sigma, right? So just the idea that if we want to know everything there is to be known about a distribution, if it's binomial, we just need to know n and p. If it's uniform, we just need to know a and b. If it's normal, we just need to know mu and sigma. And mu and sigma are what they've always been, the mean and the standard deviation. If we're asked about the variance, it's just the square of the standard deviation. So the normal distribution is seen very frequently because a lot of things are actually normally distributed. So heights, size of things produced by machine, errors in measurement, blood pressure, marks on a test. And so, by the way, if someone says, oh, they're grading on a curve, that's actually a bad thing. Well, depending on who you are. Grading on a curve means very few people get A's, most people get C's, some people get B's, right? So you're grading on a curve so that the majority of your people, of your students rather, get C's. So even if the scores are very tight and everyone gets like between an 80 and a 90, only the top echelon of people are actually going to get an A grade. That's grading on a curve. Sounds terrifying. So one of the things that we're going to use for our normal distributions is something called the empirical rule. And what that tells us is that we can look at how many standard deviations we are from the mean and get an idea of the percentage or the probability or the likelihood of values in that range. So if we look first here, it says about 68% of the x values lie between one standard deviation of the mean. So if I'm here at the mean mu, I can go forward by one standard deviation, or I can go back by one standard deviation. In this region here, remember that area equals probability. This region here contains 68% of all of the values. Now, because this is a symmetrical curve, that means 34% are here and 34% are here. We also have that 95% of the x values are within two standard deviations of the mean. So what that means is that from the mean, I can go up to standard deviations, or I can go down to standard deviations. And the area of this region is going to be 95%. Right, so 95% of all the X values are going to be here. So this is 95%, the whole purple region. And because we're symmetric about the mean, we will have half on one side and half on the other. So 47.5% are over here and 47.5% are over here. The last tier is going to be for the 99.7%. So 99.7% of values, X values, lie within 3 standard deviations above, within 3 standard deviations of the mean. So what we take that to represent is I can go up 3 standard deviations and down 3 standard deviations. In this area here, most of our values are going to be within 3 standard deviations. And by most, I mean 99.7%. So we have 99.7% of values are in this blue area. And because we're symmetric about the mean, we have 49.85% on the left, on the right, and we have 49.85 on the left, right? So we can always split things down the center after each. So let's see if we can use this to solve a problem. So in our example here, we have 95% of students are at school are between 1.1 meters and 1.7 meters tall. 95%. So remember, let's go back up a little bit and let's look at our empirical rule. And let's see if we can shade this in one more time with purple. 95%, that's that 2 standard deviation. Right, so that was here. And our mean is always in the middle, always, always, always. So 95, that's going to give us 2 standard deviations. So that's going to be from here to here. And we actually know the ending values for this, right? Because they're telling us that these 2 standard deviations, this purple region, it's going from 1.1 to 1.7. So this is a bit of a challenge problem to start off with. I think things will get easier once we kind of pin down what we're doing. But first of all, mu, the mean, is exactly in the middle of these 2 values because of symmetry. So how can I figure out where exactly in the middle is? There's 2 things I can do. 1, I can find the midpoint. I think I'll call this A. I can find the midpoint, which is going to be 1.1 plus 1.7 over 2, which is 2.8 over 2, which is 1.4. And so this is the mean. The other thing I can do is I can kind of use distance, the idea of distance. So I can look at the distance between 1.1 and 1.7. So if I want to go from 1.1 to 1.7, I have to add 0.6. And then to get to the midpoint, I just want to go half the distance. So half the distance is 0.3. So I just want to go 0.3, go halfway. So 1.1 plus 0.3 gives me 1.4 as well. So this might feel more intuitive, but what we did in method A is certainly faster and we get the same result, which is good. So we computed the mean, check. And we need to compute the standard deviation. So now there's a couple ways we can do this. We can use the 1.7 or we can use the 1.1. So how shall we look at this? We should probably write down what the mean is, right? We know the mean is 1.4. So if I'm at 1.4 and I go up 2 standard deviations, this is mu plus, mu is the mean, it's my starting point, and then I'm going up plus 2 standard deviations, which is 2 sigma. So we know that mu plus 2 sigma, that needs to get us to 1.7. Well, we know what mu is 1.4. Still don't know what sigma is, but I'm feeling like we can find out. So let's go ahead and subtract 1.4 from each side. So now I have 2 sigma equals 0.3. And next, I'm going to divide each side by 2. So I get sigma equals 0.15. So now we're done. We had mu equal to 1.4, sigma equals 0.15. And if I really wanted to put a nice little bow on it, I would say x is normally distributed with mean 1.4 and standard deviation 0.15. So next, we're given a random variable. It follows a normal. There's a space there. It follows a normal distribution with mean mu and 30 and standard deviation 6. So this is saying x follows a normal distribution with mean 30, standard deviation is 6. So what range of outcomes are within 1 standard deviation of the mean? So we want to kind of look at this maybe graphically at first. So here's our normal-ish curve. We know the mean is always at the center. And that mean is given to us as 30. And we want to go 1 standard deviation from the mean. So I'm going to go plus 6, because 6 is my standard deviation, and I'm going to go minus 6. So if I'm at 30 and I go up by 6, that'll put me at 36. And if I go down by 6, that'll put me at 24. The other way you could look at that as mu plus sigma, mu minus sigma. So that was 30 plus 6 giving me 36, or 30 minus 6 giving me 24. So the range of outcomes that are within 1 standard deviation of the mean are here. All right, so let's look, what about 2 standard deviations of the mean? So I want to look again, kind of at the curve. I know that my mean is always at the center, so I have mu equal to 30. But this time I want to go up, so we did one standard deviation last time, but now I want to do 2 standard deviations. So I'm going to go up and up again. So I'm going to do +6, and then I'm going to go up another +6 because 6 is my standard deviation. So if I'm at 30 and I go up 6 2 times, that's going to put me at 42. Similarly, I can go back as well. So I can go back 6, right? So that's minus sigma, and back another 6, minus another sigma. So if I'm at 30 and I go back 6, that puts me at 24. If I go back another 6, that's going to put me at 18. Right? So 18 to 42, that's the range of outcomes that are within 2 standard deviations of the mean. I could also look at it as mu plus 2 sigma and mu minus 2 sigma. So again, that's 30 plus 2 times 6, giving me 42, or I could go to the left, mu minus 2 by 6, giving me 18. So the range 18 to 42, that's within 2 standard deviations of the mean. All right, so for the last one, I want to do 3 standard deviations. So again, the mean and mu always at our center. It was given to us to be 30. So I've got 1 standard deviation, another standard deviation, and another standard deviation. So I can go +6, that's 1 standard deviation, plus another 6, that's 1 standard deviation, plus another 6, that's another standard deviation. So if I'm at 30 and I go up 6, 36, I go up 6 again, I'm at 42. I go up yet another 6, now I'm at 48. Similarly, I can go back 6, which is a standard deviation. I can go back another 6, and then I can go back for the 3rd time. So 6, going back 6 puts me at 24. Going back another 6 puts me at 18. Going back another 6 puts me at 12. So I could also think of this algebraically as mu plus 3 sigma and mu minus 3 sigma. So that's going to be 30 plus 3 times 6, which gives me 48. And I'm going to the left. So the range from 12 to 48 represents being within 3 standard deviations of the mean. So remember that we have our empirical rule. What does it say? 68% of values are within 1 standard deviation. 95 are within 2, 99.7 are within 3. So let's go ahead and label those just for fun. So we've got 68. We've got 95. And we've got 99.7. All right, so now we have kind of a trick question. How many standard deviations away from the mean is the value 20? Oh, okay, so let's look again at what our distribution looks like graphically. The mean, always at the center. Mean is 30, same problem, right? I know that if I go up 1 standard deviation, I'll be at 36. I know that if I go down 1 standard deviation, I'll be at 24. I can kind of spread my wings a bit further here. I can go up another standard deviation, and that'll put me at 42. And I can also go down another standard deviation, and that'll put me at 18. Where does 20 fall into this? Well, 20 is definitely in between 18 and 24. So I'm looking at about here. Here's 20. Well, 18 was 2 standard deviations away from the mean. 24 was 1 standard deviation away from the mean. So we're expecting 20 to be like 1 and something, right? 1.5, 1.3, something like that. Standard deviations away from the mean. But how can we know for sure? Well, let's think about it. If I start at 30 and I add a certain number of standard deviations, right? So this represents starting at 30, and then I'm moving in terms of standard deviations, right? So like every step would be a standard deviation. How many of those steps do I need to take to get to 20? Well, we know that standard deviation is 6. I still don't know how many steps I have to take, but I know that each step is 6. So now I'm going to solve this for our unknown quantity. So I'm going to subtract 30 from each side. And then I'm going to divide everything by 6. So what I end up getting is negative 5 over 3, or negative 1.67. And that makes sense because when we subtract a standard deviation, that means we're going to the left. When we add a standard deviation, that means we're going to the right, relative to the mean, of course. So we know we didn't go a full 2 standard deviations, because if we had gone a full 2 standard deviations to the left, we would be at 18. And if we had gone only 1 standard deviation to the left, we would have been at 24. So we went 1 and part of another 1. That's how many standard deviations we went to the left, 1 and change. In particular, 1 and 2/3 of a standard deviation. So that's kind of the tricky way to solve it. Typically what we can do is we can convert a normally distributed random variable x with mean, mu, and standard deviation sigma. We can convert it into what's called the standard normal. So normal is, right, so we've got like regular normal. That's not the official name, just FYI. Right, so mu and sigma are just numbers that are given to us. For the standard normal, we're given that mu is equal to 0 and sigma is equal to 1. So it's standardized. And this is a way that you can take data that maybe has varying means, like you want to compare 2 things of data, but you know, maybe the mean for one is 10 and the mean for the other is 13, and standard deviation for the first guy is 2, but the standard deviation for the other guy is, you know, 1.8. Well, how can you compare them? And the way that you do that is you actually kind of scale them down, you standardize them. And this is the idea of a z-score. So for a z-score, what happens here, if x is normally distributed and we have mu and sigma, then the z-score is equal to x minus mu over sigma. And basically what this is, z equals the number of standard deviations that x is away from the mean. So let's look at example D again from the previous, right? So we said how many standard deviations away from the mean is the value 20, right? Like 20 is blank standard deviations away from the mean. That's what we're trying to answer. Well, let's look. We knew that x was equal to 20, right? That was given. And we know that for our problem, mu was 30, and sigma was given to us at 6, right? So remember here that X was following a normal distribution with mean 30 and standard deviation 6. So that's why I got those. So if I want to know how many standard deviations how many standard deviations 20 is from the mean, I can just plug it into this handy formula. So I've got 20 minus 30 over sigma, which is 6. And again, we'll see that this is negative 10 over 6, approximately negative 1.67. Maybe you're wondering, well, how did that work? So let's think about it. Let's go back to the first time we did this problem. First time we did this problem, we said 30 plus some number of standard deviations sigma was equal to 20. Well, here I'm telling you that Z is the number of standard deviations. So let's go ahead and replace this with Z, right? It's the number of standard deviations. So if I wanted to solve this for Z, I would do 6 times Z, 20 minus 30. So Z equals 20 minus 30 over 6. Well, guess what? 30 is mu, 6 is sigma, 20 is X. So it's not at all different from using X minus mu over sigma. If your Z-score is negative, right, you're a negative number away from the mean, that means you're going to the left. If you're positive, that means you're going to the right. So let's go ahead and see if we can use our Z-scores to determine some of these values here in the examples. So here we want to find the Z-score when X equals 17. So we always have Z equals X minus mu over sigma. We have that mu equals 5 and sigma equals 6. So I have, oh, and they're giving me that X is 17 for this case. So I've got 17 minus mu, which is 5, divided by sigma, which is 6. So that gives me 12 over 6, which equals 2. So 17 is 2 standard deviations, and 2 is positive, above the mean. All right, so let's do it again, but now we're going to use 1. So again, we've got Z equals X minus mu over sigma. X is 1, mu is 5, sigma is 6. So we've got negative 4 over 6, which is approximately negative 0.67, right? Because this is negative 2/3. So that means that oh, that was supposed to be 17. Maybe let's try doing it with a little correction here. Perfect. So this means that 1 is negative 2/3 standard deviations below, right? Because it's negative. So I could put a decimal, I could put a fraction, it doesn't matter. Right, so you just use this formula to convert your normal to a standard normal, right? So if X follows a normal distribution with mu and sigma, then Z follows a standard normal with 0 and 1 where z equals x minus mu over sigma. So this is kind of what I was hinting at earlier, is that when we standardize by using the z-score, we can compare data more easily. So if x is normally distributed with mu 5 and sigma 6, find the value that is 2 standard deviations above the mean. So find the value that is 2 standard deviations above the mean. So this means that z is 2. Let's look at the next example. Suppose that y follows a normal distribution with mean 2 and standard deviation 1. Find the x value that is 2 standard deviations above the mean. This means the same thing. Z is 2, positive 2, right? So what we're going to get is that 2 equals, find the x value. Find the x value, right? I'm going to turn this into a y. Right, so we don't know. So 2 equals x. I don't know what x is, but I do know mu. Mu is 5, and sigma is 6. Similarly below, I'm going to have 2 equals, I don't know what y is, but I do know that mu is 2 and sigma is 1, right? And so I'm getting those values from here and from here, right? My mu and my sigma. So I can go ahead and solve this equation. I'm going to multiply both sides by 6. So I get 12 equals x minus 5. If I add 5 to both sides, x equals 17. So 17 is 2 standard deviations above the mean. Similarly, in the second part with y, and dividing by 1, that does nothing. So I get 2 equals y minus 2. I add 2 to both sides, and I get that y equals 4. So now I can kind of compare and contrast x values and y values because they're both normally distributed. Granted, they don't have the same mean and standard deviation, but I can now say, you know, whether or not certain values are within a certain range or if they're outliers or not. All right, so for this next example, we're going to be relying on z-score and the empirical rule. So let's just kind of briefly recap the empirical rule. So we know that within 1 standard deviation, we have 68% of the probability. But if I'm standard normal, 1 standard deviation is just 1 times 1. My standard deviation is 1. So z equals 1. Okay, within 2 standard deviations, I'm going to get 95%. Well, if I'm standard normal, 2 standard deviations just means I'm at 2. And within 3 standard deviations, I'm at 99.7%. But in a standard normal, this is just 3. So this is the case where we're looking at normal 0, 1. And then this is just in general. So, for example, 6.6. From 1984 to 1985, the mean height, what does that mean? I'm going to write mu. The mean height of 15 to 18-year-old males from Chile was 172.36. Okay, so my mean is 172.36. The standard deviation was 6.34. Let Y be the height of 15 to 18-year-old males in Chile from 84 to 85, right? So then we can see here, Y follows a normal distribution with mean, as we identified, 172.36, and standard deviation 6.34. So now we want to figure out what range of values are going to contain 68% of the data. So remember that 68% of the data corresponds with a z-score of 1. 95% of the data corresponds with a z-score of 2. And 99.7% of the data corresponds with a z-score of 3. So all I want to do is I want to convert these z-scores into x values, right? So I want to say, okay, well, 1 equals x minus the mean, mu, 172.36 divided by 6.34. So I'm going to multiply each side by 6.34. And then I'm going to add 172.36 to each side. And I get 178.7. This equals x. But there's something kind of hinky going on here because it's asking us for 2 values. So let's think about that. What 2 values? Well, let's look at it from this graphic again. We know our mean is 172.36. And if I go up 1 standard deviation, that's going to give me 178.7. But the question is within 1 standard deviation. So I can actually also go down 1 standard deviation as well. And that's going to give me 166.02. So where does that come from? Where does that come from? How come our equations aren't set up like that? Well, remember that +1 is above the mean, and we also have the case of -1. That's going to be below the mean. So I can just solve the same equation for z being -1 as well. So that's going to give me -6.34 equals x minus 172.36, and that gives me 166.02 equals x, right? So you've got to do the plus and the minus. So we're going to have 2 equations here. We're going to have, for the second guy, for 95%, we are going to have two equals x minus mu, which was 172.36 over the standard deviation 634. So 6.34 times 2 gives me 1268. This equals x minus 172.36. So I'm going to add 172.36 to each side. 185.04 equals x, right? So that was for the +2. I also need to do minus 2. So now I have x minus 172.36 over 6.34. I'm going to solve it so I get negative 12.68 equals x minus 172.36. And I get 159.68. So 68% of the y values lie, okay, whatever, y, x, who cares, lie between 166.02 and 178.7. Their z-scores are -1 and +1 respectively. For the next part, 95% lie between 159.68 and 185.04. Z-scores are -2 and +2 respectively. So you can go ahead and solve it for when z equals 3. It's the exact same thing. I'll leave it to you. So the last example, the scores on a college entrance exam have an approximate normal distribution with mean 52 and standard deviation 11. So this is very much the same thing. So I'm going to show you maybe a little bit different way to solve it. We did it with the z-score formula, but let's just look at it kind of graphically. So when you can do things like this without having to memorize formulas, you're in much better shape, I think. So our mean was 52. And then we've got our standard deviations was 11. So that means if I want to make a hop to the right, I'm going to go up by 11. So 52 plus 11, that puts me at 63. If I want to go up another standard deviation, that's another step, that's 11. That's going to put me at 74. If I want to go up another standard deviation, I got to go up 11 again. That's going to put me at 85. Similarly, I can go back. So we're just making our little hops. And each hop is 11. So if I'm at 52 and I go down by 11, that puts me at 41. I go down by 11 again, that puts me at 30. I go down by 11 again, now I'm at 19. So if I'm within 3, that's the full shebang almost, right? So that's going to be 19 to 85. I'm doing this backwards now. 19 to 85. And that's -3 and +3 for my z-scores. Remember, z-scores, z-values, they count the number of standard deviations away from the mean, right? So if I'm at 85, I'm 3 standard deviations above the mean. If I'm at 19, I'm 3 standard deviations below. Okay, for the next one, 95%, that's just going to be within 2 standard deviations. So that's going to be from 30 to 74. And that's going to be left 2 or right 2. And then for the last one, within 1 standard deviation, that's 68%, that's going to be 41 to 63. That's going to be to the left 1 standard deviation or to the right 1 standard deviation.